The formula above is for the effective charge that a valence electron experiences when it's in an atom. In the formula, Z stands for the actual number of protons in the nucleus. That is also the actual positive charge that the nucleus would hold. And S stands for the shielding that other electrons besides the valence electron in question can provide. So we can look at an example down here. Sodium is shown on the left, and in the Bohr model for sodium, there will be 11 protons in the nucleus. There would be 2 electrons orbiting around that nucleus in the first energy level. Then we had said that there would be 8 electrons in the next energy level. Since sodium is found in the first column of the periodic table, it will have 1 valence electron, so that is 1 electron that's in the highest energy level. Now we want to find out what net charge does that valence electron experience from the rest of the atom. A charge can't exert a force on itself, so we're really just going to consider all the stuff inside this boundary. Now, electrons that are not valence electrons, that are at an end that's less than the outer ring here, they're going to be called core electrons. And core electrons can provide shielding from the nucleus, meaning their charge will somewhat cancel with the nucleus's charge. Now, if we were doing a simple subtraction to find the net charge within the red boundary here, we would do plus 11 for the nucleus and then minus 10 for the core electrons. However, what this formula shows here is that the core electrons do not provide a full -1 when it comes to canceling the charge of the nucleus. Instead, they're going to provide 0.85 times the number of electrons when it comes to the shielding that they provide. So let's calculate the shielding that the core electrons of a sodium atom provide. The formula is S equals valence electrons times 0.35 plus core electrons times 0.85. Now, for this particular calculation, we will consider that there are no valence electrons. This is because we're trying to see what net effect the rest of the atom has on this outer valence electron. The valence electron cannot exert an effect on itself, so we'll actually consider there to be no other valence electrons in question. There are, however, 10 core electrons. If we multiply this, we find that the shielding is going to be 8.5, and we can go on to the next step, which is to find the effective charge that the atom exerts on the valence electron. So that formula is often written as ZEFF equals Z minus S, where Z is the atomic number and S is the shielding, or we could rewrite it as Z minus the valence electrons times 0.35 and then minus the core electrons times 0.85, the idea being that the electrons contribute a negative toward the charge and the protons contribute a positive number. So we'll have plus 11 minus 0 minus 10 times 0.85. So this is 11 minus 8.5, which gives us a final effective charge of plus 2.5 for sodium. Magnesium is similar. It has 10 core electrons, but we see that magnesium is actually in the second column of the periodic table. It is here, so it'll have 2 valence electrons, and that's seen in the picture here. So when we do the calculation, it ends up being a little different. Now when we try to find out what effect the rest of the atom has on one valence electron, we do want to consider the other valence electron as contributing some effect. So let's say that the shielding will be the valence electrons times 0.35, and then we'll add the core electrons times 0.85. Now, when it comes to the valence electrons, we don't include the one in question that we're trying to see the effect on. We just consider the rest. So we're going to just use 1 valence electron for magnesium. This is magnesium. So let's do 1 times 0.35, and then we'll add in the 10 core electrons times 0.85. The shielding then becomes 8.85. So to get the effective charge, we'll do Z minus S. Magnesium actually has 12 protons in its nucleus. We can see that here in the atomic number for magnesium, 12 protons. And then we'll subtract our 1 times 0.35, and subtract 10 times 0.85. So for magnesium, I get an effective charge of 3.15. What this means is that a valence electron is going to feel more strongly attracted to a magnesium atom than it will toward a sodium atom. And when the valence electrons are more attracted, what happens is the atomic radius decreases. This table gives atomic radii in picometers. And we can see that for sodium, it's got a value of 160 picometers for its radius. Magnesium has a value of 140 picometers. And so magnesium's a smaller atom. The reason why is because those valence electrons are attracted more to the magnesium atom than they are to the sodium atom. And that's a trend we'll see, that as we get more and more valence electrons on the atom, there's going to be a stronger attraction. Also, as we go down the column, we find that there are just more energy levels. So we've got an n equals 1 up here. Down here we have n equals 2, n equals 3. The more energy levels you create, the larger the atom becomes as well. So those are 2 trends that we'll see when it comes to the sizes of the atoms.